This video lesson is going to center around naming and writing formulas for ionic compounds. Some prior information from last unit that you'll need to know in order to be able to do this is going to be remembering where your metals and nonmetals are and what charge different atoms will form. If you recall, the metals are located on the left side of the periodic table and the nonmetals are located on the right side of the periodic table. They are separated by the staircase, and that is where you can find the metalloids. The charge that atoms form depends on how many valence electrons they have. So atoms that have 7 valence electrons, like the halogens, will form a -1 charge to get their full octet of 8. These guys have 6 valence electrons, so they form the -2 charge to get their full outer shell of 8. On the other side, these have 1 valence electron, so they will lose that electron to get their full octet. All of these charges can also be found on your periodic table as well. An ionic compound can be defined as a metal bonding with a nonmetal, or another way to say this is a cation bonding with an anion. Cations, if you recall, have a positive charge. Anions have a negative charge. If you look at your periodic table, all of the metals form positive charges, while the nonmetals form negative charges. So either of these definitions will work. Again, if you recall, all atoms want a full outer shell, so 8 valence electrons. So they're going to bond in order to achieve that. So for example, potassium generally has 1 valence electron, so it'll form the +1 charge. Chlorine has 7, so it likes to form the -1 charge to gain 1. So if potassium gives its electron to chlorine, now they both have a full outer shell. This is how ionic compounds will form. One will give and one will take, so they can both have their full outer shell. Let's look at some other examples of metals and nonmetals coming together. If you look at your periodic table, you'll see that calcium tends to form a charge of +2 due to its 2 valence electrons, and oxygen has a -2 charge because of its 6 valence electrons. It'll gain 2. +2, -2, these charges balance out, they equal each other out. These two will come together to form the compound calcium oxide. Whenever we write these out, it's important to know that we always list the metal first and then the non-metal second. So you would never see it written out like this. That's bad. We don't do that. So metal, non-metal. So for this next example, notice how we've got lithium. Lithium forms a charge of +1. Fluoride is -1. +1, -1. They equal 0. They balance each other out. These will come together to form the ionic compound lithium fluoride. If you look at your periodic table, there are a ton of combinations of these. So how do we handle it when the charges don't match? For example, aluminum forms a charge of +3, if you look at your periodic table, and chlorine is -1. These charges do not match. Aluminum would like to lose 3 electrons to become stable, where chlorine would just like to gain 1 electron to become stable. So aluminum could give 1 to chlorine, but it still has 2 other ones it would like to remove. So, can these still bond? Yes. In order for this to work, you would just need to get more chlorines. If you have a total of 3 chloride ions, each with a charge of -1, notice that the overall charge on this side is now -3. If you maintain the 1 aluminum, that still has a +3 charge. +3, -3, these equal 0, they balance out. This will come together to form the compound aluminum chloride, and this is how we write this out. You still write the metal first, non-metal second, and since I needed 1, 2, 3 chlorides to balance out the charge, I will write AlCl3. We refer to this as a subscript. So subscripts tell you how many of a particular atom you have. We write it after the atom, so there's 1 aluminum and 3 chlorines. Let's try another one where the charges don't match. So if you look at your periodic table, sodium has a charge of +1, and oxygen has a charge of -2. So what this means is sodium wants to lose 1, but oxygen needs to gain 2. So while sodium could lose its 1 electron to oxygen, oxygen would still need 1 more. So how can we solve this? Adding another sodium. Since that sodium has a charge of +1, if you overall have 2 sodiums, you've got a charge of +2. The one oxygen has a charge of -2. These balance each other out. So now I've got 2 sodiums, so I'd write this as Na2O. Writing in a subscript, showing that I need 2 sodiums. This also works if the charges are a little different. So strontium is +2, where nitrogen is -3. So the problem here is if I add another strontium, that strontium has a charge of +2. So 2 + 2s, that's an overall charge of +4. That still doesn't equal -3. So what you can do is you can try to find the least common denominator. Basically, what's a number that both 2 and 3 go into? 6. Meaning, if I added another strontium, the overall charge here is +6. If I add another nitrogen, that overall charge is -6. +6 - 6, that equals 0. It balances each other out. So I would write this one as Sr3N2 because I needed 1, 2, 3 strontiums and 2 nitrogens to balance that out. So for this one, I needed 2 subscripts to help me out. So whatever you need to do in order to get the positive and the negative charge to equal each other and to equal 0, the compound can still form. Another way that we can show this transfer of electrons is to write out the Lewis dot structure. So the Lewis dot structures were invented by a guy named Lewis, and they involve dots. Simply, the number of dots is equivalent to the number of valence electrons. If you recall, you can figure out valence electrons by looking at your periodic table. Everybody in group 1 has 1. Everybody in group 2 has 2. Skip group 3, 4, 5, 6, 7, and 8. So neon is a noble gas, so it has 8. So for the Lewis dot structure, I would draw 1, 2, 3, 4, 5, 6, 7, 8 dots. Chlorine, I would draw 1, 2, 3, 4, 5, 6, 7 dots. Potassium, I would just draw 1. So here are examples down here for 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons, 8 being the most you can have. I realize that the dots are kind of written in a funky order. That's something that we're not going to really get into. Basically, at the end of the day, as long as you've got the correct number of dots, you're good to go. What's nice about the Lewis dot structure is it gives a visual representation of one of the atoms giving an electron while the other one takes. So for example, potassium has 1 valence electron because it's in the first group, so 1 dot. Chlorine has 7 valence electrons, 7th group, so I draw 7. Looking to see what charge they form, potassium tends to form a charge of +1. It likes to get rid of that electron. Chlorine has a charge of -1. It likes to gain that electron. So we can physically draw potassium giving that electron to chlorine. For calcium and oxygen, calcium has 2 valence electrons. It's in the 2nd group. Oxygen has 6. It's in the 6th group. Calcium likes to form a charge of +2. It likes to lose those 2. Oxygen has a charge of -2. It likes to gain those 2. So we can physically draw those dots traveling to oxygen. This works because ionic compounds bond through electron transfer. So they physically give electrons one to the next in order to get their full octet. Here are a couple more examples where we can draw the Lewis dot structure and we can show that electron transfer. So lithium fluoride, you would draw a lithium and a fluoride. Lithium has 1 valence electron. Fluorine has 7. Again, I'm just looking at what group they're in. Lithium forms a charge of +1. Fluoride is -1. Gain 1, lose 1. Lithium will lose for fluorine to gain. Everybody's got a full octet. Everybody's good. For aluminum chloride, you draw an aluminum. And remember how we had to have 3 chlorides in order for the charges to balance out? Well, then I will have to physically draw 3 chlorides. It doesn't matter where you draw them. Aluminum has its 3 valence electrons. It's in group 3. And each chlorine has 7 valence electrons. So I'm going to draw 7 dots around each one. When you check the charge, aluminum has a charge of +3. It wants to lose all 3. Each chlorine has a charge of -1. Remember, that's how they balance out, +3, -3. So how this works is aluminum gives 1 electron to each chlorine. So aluminum lost all 3, each chlorine got its 1, now everybody's got the full octet. So for sodium oxide, for this one you would draw 2 sodiums, because it's Na2, 1 oxygen, each sodium has 1, the oxygen has 6, again I'm just looking at what group it's in. Sodium likes to form a +1 charge, oxygen is a -2. Again, the charges balance out. So the sodiums will each give their electron to oxygen. Everybody has their full octet. So when I show this slide in class, it's actually a GIF and it shows the transfer. So I'm sorry that this is not the same effect. But basically, sodium will give its 1 electron to chlorine. Sodium now has a charge of +1, chlorine has a charge of -1. And so what happens here is something called an electrostatic attraction. Meaning, you know how sodium's got this positive charge and chlorine's got this negative charge? Positive and negative charges attract. So what holds this compound together is purely an attraction. So it's not even really a bond per se. They're kind of like magnets. So they're magnets that are coming together and they're attracted to one another, which will become important later on when we talk about how this type of compound varies from other compounds. So for now, all you need to know is that this is held together by an electrostatic attraction due to the electron transfer that occurs. You might have noticed throughout the video that I was naming these compounds. So for example, KCl, we wouldn't just say KCl, we're better than that. But you don't say potassium chlorine either. The rule works like this. The metal's name doesn't change, so you literally just say the name of the metal. So KCl, you're just going to say potassium. Remember, the metal's always listed first. Then you've got the nonmetal. The only thing with the nonmetal is you need to make sure that the nonmetal gets an "ide" ending. So rather than chlorine, we say chloride. So for Na2O, metal's name doesn't change, sodium. And then we'd say instead of oxygen, oxide. It does not matter how many there are. So you literally just say metal and then the nonmetal with an "ide." And that works for like 80% of ionic compounds. There is a couple of exceptions. If you could look on your periodic table to the metals located in the D block or those transition metals, you may have noticed that some of those elements have multiple charges on them. So for example, if you look at copper, copper has a +1 written on it and a +2 written on it. Basically what that means is copper has 2 different ways to become stable. Copper can lose just 1 electron to become stable, or it can lose 2. Why? It has to do with those D block electrons. Things just kind of get weird once you add those D block electrons into the configuration. It's not something we're going to dive too deep into, but it's something that we do need to work with. Because if we had copper with chlorine, and it was copper with a +1 charge, I would just write CuCl. If I did copper with copper +2 with chlorine, it would be CuCl2. 2 totally different compounds. They react differently, behave differently, etc. Well, here's the problem. Based on what we just learned, we would name both of these copper chloride. So if I'd call them both copper chloride, how do I differentiate? That's what we're going to talk about next. The first thing that will be helpful is to figure out what charge an element even has. So for example, if you look at your periodic table, you will see that chlorine has a -1 charge. And if you look at iron, you will see that iron could be +2 or +3. Those are the 2 options. So we can do some backwards math to figure this out. There are 2 -1 chlorines. So 2 -1 chlorines means there's an overall charge on this side of +2. Now, in order for this to be an ionic compound, it has to be neutral. The charges have to balance out. So if that side has a charge of +2, and my choices are +2 or +3, I'm going to go with iron +2. So in this example, iron is a +2. Other examples, it could be a +3, but in this case, +2 is what balance out the charges. For this one, we're going to do the same thing. So sulfur has a charge of -2, and if you look at your periodic table, tin can either be +2 or +4. Again, backwards math. So over here, I have 2 -2s. So if I have 2 -2 sulfurs, that ends up being a charge of -4. Again, I need these to match. So if I have 2 -2s, the one that's going to make the most sense is a +4. So this is how you can figure out which charge a particular compound has just by looking at it. What we still need to figure out is how we're going to write out the name of the formula. So once we know what charge the metal has, now we can incorporate that charge into the name. So again, the old rules were this. You just say the name of the metal, so I would say iron. And then you say the name of the nonmetal with an "ide" ending. So rather than chlorine, I say chloride. Here's the new part. So since iron is one of the metals that has multiple charges, I need to include something in the name to communicate which charge it is. If you recall, we had decided that iron was a +2 charge. So the way that I'm going to say it's +2 rather than +3 is this. I'm going to include a Roman numeral in the name that matches the charge of the metal. So I'll say iron 2 chloride. For the next one, Sn is tin. Sulfur becomes sulfide. And now, since tin is one of those elements with multiple charges, I'm going to include a Roman numeral in the name that represents the charge. We had picked +4 because that matched to the other side, so the Roman numeral I'm going to include is going to be a 4. A quick rundown of all the Roman numerals in case you need a refresher. It goes 1, 2, 3, 4, 5, 6, and that's about as high as we'd go. So for these ones, whenever you have a metal with a multiple charge, you need to include a Roman numeral. So to reiterate the rule one more time, whenever you have a metal with a multiple charge, you need a Roman numeral. So for SnCl2, I would say tin, and then I would say chloride. I'd look at my periodic table and I would notice that tin is one of the metals that has multiple charges. Therefore, I need a Roman numeral. Now this is where I'm going to do that backwards math to figure out which one I'll do. Chlorine is a -1, and there's 2 of them. Tin can be +2 or +4. Because there's 2 -1 chlorines, tin must be a +2 in this example. So the Roman numeral I'm going to include is a 2. For the next one, Fe is iron, so I'll start off with iron. Oxygen, I'd put oxide. And now, since iron is one of those metals with multiple charges, I'll do the backwards math again. Oxygen has a charge of -2, and iron can be +2 or +3. This one's going to be a little bit harder. There are 3 -2 oxygens. So if there's 3 -2s, that's going to be an overall charge of -6. Now, I already have 2 irons. So would it make sense to have 2 +2s or 2 +3s? In this case, 2 +3s, because that also equals 6. So I'm going to include a Roman numeral of 3. Just to be clear, we only do this for metals that have multiple charges. So for example, NaCl. Na is sodium, so I'd say sodium. Cl is chloride. I'd look at my periodic table and see that sodium is only a +1. It doesn't have multiple charges, therefore I don't need to include a Roman numeral, so I just leave it as sodium chloride. That concludes how to name and write formulas for ionic compounds. You can find some additional practice on Canvas.